All right. Yeah, so I'm Chris. I'm a software engineer at Google. I work full-time on making LinuxBoot a reality. And I think we're going to split this talk in kind of two parts. The first one being a recap of what is LinuxBoot and why are we trying to do this. I imagine a whole bunch of you actually already know that part. The second part is going to be us talking about some advancements we've made in the last 6 months in booting other operating systems. And then I'm going to try to talk about some crazy shit. And I imagine there's going to be a bunch of people in the room that will tell me this is totally impossible. Now, I should credit my most recent intern, Max, who actually did most of the work that is new that I'm going to present later. Unfortunately, he's already left, so he can't actually be here to present with me. So I guess to start with, we can look at the state of the world today. This is kind of what UEFI looks like on most systems, and UEFI is usually your normal x86 firmware. If you look at the two columns on the left, right, this is like CPU initialization, chipset initialization, stuff like that. That tends to be, closed source blobs supplied by Intel. These are probably core IP things that they don't want to release. But as we move further to the right, we'll see more things that I think, I'm going to say, kind of resemble an operating system, and B, mostly consist of things that aren't actually supplied by Intel. If you look at that, like, there's a whole bunch of drivers that are usually called Dixies, DXE, which I don't remember what that stands for. And you have a scheduler that figures out when to run which driver and how. And some drivers might actually look like device drivers, and some drivers might look more like applications. And if you put this together like in a worldview, you'll see it looks a lot like an operating system. Now, most of these parts are to the general open source world closed source. Many of them might actually be based on open source pieces from EDK2, Intel's reference implementation. But there's no guarantee that that's actually true for your system. And most likely, the pieces have been changed since they were taken from the reference implementation. Another thing to notice is that while this system is very modular, that's designed such that many vendors can come together and build a system with modular parts without having to reveal core IP to each other. So sometimes, like Intel doesn't actually necessarily have to reveal their binary blobs in the system to the vendor that puts together the BIOS, although it's very likely that they do, because otherwise you might not actually get a working system. So yeah, my observation is drivers, applications, scheduler looks a whole lot like an operating system. Now, all of these applications actually share an address space in ring 0. They are, as most things are, in this space written in C. And the general gist, the general opinion I have of the system, and which I don't disagree with necessarily, is that most vendors are incentivized to ship their systems and kind of forget, right? Like, you get everything working, you get all the firmware pieces together, and then you put the system out the door, and you might put out some updates very rarely to your actual users who may or may not actually pick them up, right? And from a user's perspective, if I'm just me right now, if I'm not Google, I have a hard time actually owning my own systems, right? On most systems, I can actually modify my own firmware. Most of these pieces are closed source, and I really have no visibility into them. And as a user, I probably have to guess which piece does what. You can go and disassemble it, but have a lot of fun with that. I don't think you're going to learn much from it unless you spend a lot of time on that. And the other observation is, if you have 20 plus vendors involved in actually putting together firmware like this, right? Like the independent BIOS vendors that actually do it, silicon manufacturers of hardware on the machine, devices you might put in there, ODMs and OEMs that have to cooperate to make this happen. Then if you think about actually shipping firmware updates, most normal users aren't going to go looking for these updates all the time. And I bet there's probably a lot of small companies that don't really pay attention to them either. They might pay attention if those updates come automatically through Windows or Red Hat or Debian or some, their OS. So on top of, getting all the people together to actually ship new firmware, you also have to find ways to actually get it to the user if you care about that. The observation as kind of an outsider is that these are kind of black boxes that wrap other black boxes. And if I were to look at this and say, like, what do you think happens to a typical vulnerability that you find in firmware? With that many people involved, with that many organizations involved, who actually owns fixing it? Right? Is it the ODM, the OEM, or the independent BIOS vendor, or the vendor that actually has the vulnerability in their stack? How do you actually integrate it, and how do you then get it through the 3 to 5 vendors that you have to go through to actually ship that again on a normal commercial system? To me, the probability that this actually happens for everything that gets reported is pretty slim. So what we've done is we've taken the observation that this looks a whole lot like an operating system, and we've taken the observation that you can run arbitrary applications in UEFI, somewhat arbitrary, I'm going to call them. And if you take those two observations together, you can say, hey, why don't I just plug in some operating system that I already know? So what we've done is we've taken a small Linux kernel, and we embed it in UEFI as a UEFI application. It gets wrapped in a little PE32 executable header. It looks just like a normal PE32 executable to UEFI, and when it goes to run it, that's what you actually get, right? You get Linux. Now with Linux, in the system acting as a bootloader to boot your actual operating system, there's a whole lot of pieces of the drivers that you can remove. And probably a lot of drivers that you can potentially replace with their open source counterparts. So on a lot of systems where we've done this on, let's take an example of, I think, the OCP Winterfell node. I believe we started with about 200 of those driver modules. In a pretty normal case, I think we get down to 30 to 50 of those drivers plus Linux. I think the best case that someone has actually tried out as a proof of concept is down to 5 of those drivers plus Linux. There's a couple of things that you currently just can't get rid of, or you need some other way to supply to Linux, like ACPI tables. But for the most part, you can let Linux do it. Now with Linux comes, of course, you need some kind of user space that directs what you're going to do. For us, that user space is uroot. It's a Go project where we've implemented a whole bunch of different bootloaders that look just like the ones you have today, and some that don't look like the ones you have today. So there's a re-implementation of Pixie Boot in there, for example. So some of you might say, especially those of you that have worked with Linux kernels a lot, might say, isn't Linux actually kind of worse? Or, Linux has a whole bunch of problems too. Yes, it does. But as opposed to the driver modules you're replacing, Linux is actually open. You know exactly what to expect when you put it in there. It's measurable. And you can actually reproduce the same Linux kernel if you have a binary blob and the necessary configuration, right? Linux is also pretty good in this place because Linux has drivers for everything, pretty much everything under the sun. Linux also knows how to initialize most devices on its own. Linux knows how to do PCI enumeration. These are things that you could choose another operating system for, but you'd actually have to re-implement. But Linux already has a lot of these capabilities that we need. And of course, Linux has a much larger community than UEFI does, right? There's thousands of people working on the Linux kernel every day out in the community, and there's way more. If you look at a company like Google, we have way more Linux engineers than we do firmware engineers. I imagine if you look at a lot of the cloud companies that are around today, they are going to have way more Linux kernel engineers than they do firmware engineers. Now with that, you can also think about how many SREs or sysadmins in your organization know Linux versus UEFI. An interesting side effect that we've seen on some systems like Winterfell is actually a pretty big boot time reduction. This is not necessarily a given, but can be a contributor to this being a nice replacement. If you remove a lot of the driver modules in UEFI, you're also removing the amount of time that is spent in them. Even if they weren't used in the first place, they might still be, UEFI might still attempt to run parts of them to figure out the dependency tree of which things have to run when. And on Winterfell, actually, if you remove most of those drivers, you get from an 8-minute boot time to about 20, 30 seconds. That includes, Linux coming up for a couple of seconds and then figuring out what to boot next using some bootloader. So now we have to think about Linux actually as a bootloader, right? Some of you might be familiar with the Kegs user space tool that you can use to execute another Linux kernel. But now that you have Linux and firmware, you can actually make full use of the Linux ecosystem and normal user space applications. So that means it's trivial to use modern features and modern languages in firmware. It's fairly trivial, I'm going to say, to figure out how to actually test those systems independently. Since we chose Go as our user space language, we have a pretty easy way to write unit tests for everything. And it's pretty trivial to use things like HTTP, right? It's maybe 5 lines of Go for you to put your own certificate in firmware and use that to download a kernel over HTTPS. Another hopeful benefit that we have from this is you don't actually have to run option ROMs to boot from the network anymore, right? Linux has a kernel networking driver that you can use to actually download your kernel rather than executing some random bit of code that you got from a device. What most people are probably familiar with is booting Linux from Linux, right? Kexecing another Linux kernel. Now, if we want this project to be successful in data centers, not everyone in the world just runs Linux, even though many of them do. So to actually be able to move away from UEFI solutions, we have to be able to boot other stuff. And this is something that my my intern and I and a bunch of people worked on for a while in the last couple of months is booting other things from Linux. So writing a Linux bootloader is not actually that hard, I say, having a bunch of experience with this now. That doesn't actually have to be representative of a normal bootloader. The kexec syscall basically takes, you arrange things in memory in user space the way you want them. And then you tell kexec, hey, I want these pieces of memory to be moved to these physical pieces of memory when I say go, right? And you can specify the entry point to actually jump to when you do say go. So Linux will take all that stuff, it will save it locally somewhere in its own RAM, and later you can do another system call to say, hey, I know I've saved a kernel earlier that I want you to execute, I want you to do that now. So you load a kernel, and at some point you tell Linux to go. Now, you don't actually have to deal with this to write your own bootloader all the time. We've written a bunch of tools that deal with this for you and some of the intricacies that happen. And one of the first things that we actually implemented was a multiboot bootloader. So a bunch of our contributors have been asking to boot for one tboot to do more stuff with txt and tpms. And secondly, to be able to boot hypervisors. Because not everyone runs Linux. The other thing that this is going to enable is for us to write better bootloaders for other architectures as well. Someone who's sitting in the audience back there has been working on ARM kexec for a bunch of things lately. So we'll hopefully see that soon too. Yeah, my intern spent a bunch of time hating QEMU and GDB in the last couple of months. He didn't actually hate it. He thought it was a lot of fun. I didn't, but that's probably a good division of labor. We started booting a bunch of experimental operating systems because they're open source and easier to wrangle than other things. So we've tested Akaros and Harvey. People at Facebook have used this code to boot Linux kernels with tboot. And we've also actually tested ESXi. And I'm going to show you that for a second. See if I can. So yeah, it's maybe kind of silly to boot ESXi and QEMU, but it's the best I can do for a conference right now. I pre-installed it on a disk image that I'm plugging in there already. The Linux kernel that I'm putting in there is 1.8 megs. That should fit in most firmware volumes. The NetRamFS can be as small, but because it's QEMU, I just put everything in there. All right. So you can obviously automate this part, but I kind of wanted to show you that you can easily have a Linux shell in firmware and do all the Linux things that you normally do. But booting another kernel is actually as easy as the next 3 steps. Hello? guess I have to wait a little for the console to come up. Ah, hello. All right. We actually tried to use the upstream Kegs tools to do something like this, but it turns out they have a bunch of bugs that actually don't let you boot any multi-boot operating system, and that's because some multi-boot operating systems are not especially spec compliant. So there are some special bits in there just to enable hypervisors and some other stuff. Now, the question that is on my mind after this is, okay, I can boot some hypervisors, I can boot another Linux kernel, I can boot some other random stuff if I wanted to, but the question that's still on my mind is, can I boot Windows? And how would I do that? And this is kind of where we go from some workable ideas to maybe some crazier ideas. Now, normal EFI applications, when you boot them, generally need, I'm going to say, two things. You need runtime services that will persist throughout the lifetime of the EFI application, and you need boot time services to do things that a bootloader has to do. Like, for example, try to fetch some modules from disk or do some other random stuff. For Windows, I'm going to say the main ones that it actually wants access to that are listed in the logo spec are like graphics, disk, network, and I don't actually know which ones are the hardest ones here. This is where we go into the territory of, like, I'm kind of speculating. And I kind of wonder, on server systems, which one of these do you actually need, right? Server system isn't going to have graphics. Can you stub that out? I don't know. We should totally try it out pretty soon. But the sane option here is to use Linux as an EFI chain loader, right? This is something you can do today in the upper picture. I haven't tried the lower picture. But it means that you have to keep probably a lot of parts of EFI around to actually make this work. A lot of the things that I said earlier Linux could do would now have to stay in EFI drivers that I have to maintain. That's kind of, I'm going to call it crummy. If we want to minimize the amount of code that is in EFI and maximize the amount of code that we have in Linux, this is like a solution that works, but I was really hoping for something nicer. So how, for example, could we use Linux to actually supply boot services is the question that I want to ask. And I feel like the first thing that comes to mind, my mind, which I think is not quite workable, or maybe is, but takes a lot of work, is running them side by side, right? You have a Linux kernel, it keeps running, and you execute another Ring 0 application besides it. That generally works only with resource partitioning. And eventually, of course, you want Windows to take over the whole machine. And I feel like that's likely to run into a lot of problems. Of course, if anyone here wants to try it, I would love to see that. But I think it would be interesting. The other kind of crummy part of that is in the core boot LinuxBoot combination, we would like to get rid of the RAM stage, the stage that has most of the drivers and stuff like that. To have the Tiano core payload and the boot services, you probably would have to keep all that stuff. So it's maybe not as much work reduction as we would like it to be. So I'm going to put up another picture here that I imagine is not going to work at all, but I would really like to try out with a proof of concept at some point. So I'm looking for a way to run the Windows bootloader and make system calls back to Linux to supply things like drivers, to do stuff like graphics, reading from disk, other random things. So I don't know how many of you are familiar with the Dune project from Stanford, but the Dune project was a small kernel hypervisor that used VM calls to communicate from the VM to the host. So what if you implemented boot services as small stubs that actually make VM calls to a host? You start the Windows bootloader in VMX mode. You try to emulate as much from the host as, I'm going to say accurately as you can. And when you get to exit boot services, when you stop needing boot services, you do what kexec does today. You take random bits of user space memory and you push them into the kernel and you jump to a certain starting point. I have no idea if this would work, but I would really like to try it. And I imagine there's a bunch of Microsoft people in the audience here that might be able to tell me if it's possible. So I thought I would throw this out there because it seems like a nicer division of labor between the two different kernels that might have to run side by side to actually make this work. Otherwise, we're back to the model of implementing drivers as they currently are. Yeah, so the stub implementations, I would hope, would be actually in Rust. And the VM calls to the host should look just like system calls do today in Linux, except you're using a different instruction. Of course, someone would have to write a little hypervisor in Linux to deal with this. But because the Stanford Dune project has already done that, maybe that's a good start. Anyway, from crazy ideas, I'm going to go back to what we actually think the LinuxBoot project should be. Two of the things that we find really important is we would like to give the community the tools to do what they want, but we are not here to dictate policy. And we would like for there to be security and user freedom. So security features should allow change of firmware and ownership. With that, I'm pretty much done. Thank you very much for coming.